All right, so in order to analyze anything that's dealing with conductors, the first thing we need to do is talk about conductors a little bit more. I've got a set of rules here that I use when talking about conductors, and I call them IFACs, which is an acronym for Important Facts About Conductors. Right? And for now, there are 3 IFACs we're going to talk about. We're going to talk about a 4th one later, being in a couple of weeks. So here are the 3 important facts about conductors. Important fact number 1. The electric field inside a conductor is 0 if the problem is static, if the charge is not moving around. The word static is kind of important. It won't show up now. It's not important for right now. But down the road, this will come back. If we're looking at any sort of problem that's static, fields inside the conductor are 0. I'm going to talk a little bit more about why that is over here on the left. So imagine that this block right here represents a bar of, say, aluminum. And we're going to do this basically by what's called contradiction. I mean, we're going to kind of assume there is a field inside a conductor and kind of look at the effects of that. What would that mean? So imagine this bar here is aluminum, and imagine that it does have an electric field inside of it. And I've got that electric field vector labeled E1 here. Now, if there is a field inside of that aluminum, that's going to create forces on the charges within it. And there is an astronomical amount of charge free to move. You know, again, I always go back to Avogadro's number and talk about that. You know, Avogadro's number, that's 6 times 10 to the 23rd power, in just a mole of material, the amount of atoms you're talking about is usually, you know, it's basically 10 to the 24th power, pretty close. Each of those atoms, if it's a metal, has 1 or 2 electrons free to move. So the amount of charge carriers that are free to move within this material, these are numbers like 10 to the 24th or maybe 10 to the 25th power. If there is an electric field within the conductor, those electrons are free to move. So what that's going to do is, if we have a field to the right, that's going to give us a charge configuration minus on the left, plus to the right. Because those electrons are basically going to shift over. Now, if we have a charge configuration plus minus like this charge configuration will create its own field, which would point to the left, because electric fields point away from positive charges towards negative charges. So now within the field itself, we have 2 electric field vectors to consider. The original one that I called E1, which is to the right, and this new one, which I'm calling E2 here, created by this shift in charge. The net field would be the vector sum of the 2. So the net field would be smaller than the first one. Everybody see why? Now we have a conductor with some sort of field in it still. But if there's a field in it, charge will move. Plus is this way, minus is this way, giving me a plus minus, which makes another field basically to the left. The net field is therefore smaller. And you see what will happen? No matter what, if you take this argument far enough, the field has to be 0. Because if there is a field in the conductor, charge will move in such a way that basically it will cancel it out. And there is really no limit to how much charge can move. Because, you know, again, kind of getting back to Avogadro's number, in just a mole of material, you are talking about almost 10 to the 24th electrons free to move. So in all practical purposes, there is an infinite amount of charge available to move to cancel that field out. So basically the electric field is in a conductor is 0 because if there is a field, charge will move in such a way that it will cancel that field out. It will create its own field, making the net field 0. So that's an important fact for us. I always call it IFAC number 1 for conductors. Electric fields inside are 0 if it's a static problem. Number two is really more of a logical argument here. If the conductor carries any sort of net charge, that charge will be on the outer surfaces. Now you notice I said plural. You'll see why I worded that plural here in a minute. But you know, a 3-dimensional geometry here, you know, in a sense, could have 2 surfaces. Like if you look at that problem I just handed out, there is a that shell there. See that shell? The conducting shell has really 2 surfaces, an outer and an inner. So any net charge is going to be on those surfaces because the charge repels one another. That's where it's naturally going to want to go. You know, so an example of that, if I have some sort of conducting material, and this conducting material, you got to imagine this in 3D, if it has a net charge, that charge will be on the outer surface. If it's negatively charged, this would be minus signs. And the E field inside it would be 0, IFAC number 1. Okay, IFAC number 3. At the surface of a conductor, the electric fields are parallel to the dA vector. Or another way to say that, they're normal to the surface. And let's talk about why that would be. So again, imagine this is some sort of surface right here, conducting surface. And let's imagine, for the sake of example, that there's an electric field that is not perpendicular to the surface, that the E field somehow points like this. Now remember, charge is free to move. If the electric field points like this, which way are the electrons going to want to move here? They will shift, electrons will shift left, because the field direction is defined as force direction on a positive charge. So positive charges are going to want to tend to shift this way, negatives this way. Basically what that'll do is it'll shift positives kind of in this direction, minuses in this direction. If we shift the charge configuration like this, see how we have plus minus? That creates its own electric field pointing which way? Plus minus. If I pick a point in space like right here, what does the field direction do to this positive charge here? To the left, because electric fields, they always point away from positive charge. That's just a consequence of how the field direction is defined. So this positive charge configuration would create a field here pointing left. This negative charge here would also create a field pointing left. So the net field would be the vector sum of the two. If there's some sort of field pointing left here, and I add these vectors up, you notice that the net field is something like this now. Okay. Now, if it still has a horizontal component, basically more charge moves. Makes a field to the left. See, charge will move until the net field points this way, at a right angle to the surface. Or another way to say that, parallel to the dA vector. If this is some sort of surface, the dA vector that we talk about for Gauss's law would point this way. Because the dA vector, by definition, makes a right angle to the surface. So that's IFAC number 3. It's very important that we have a good grasp on these things and why, because I'm going to refer to these quite a bit when we go through some of these examples. All right. So those are the IFACs, the first 3. There's a 4th one coming when we talk about electric potential here in about a week. But for now, I think what I'm going to do here, for the sake of file management,